I'm very, very excited to be here. Thank you very much for the introduction. So my name is Philipp Langer. I work with Eclipse Source. I'm a software architect and a general manager in Vienna. And what Eclipse Source does is basically it's an open source technology and service provider working with our customers to build all sorts of tools, custom IDEs, domain-specific modeling tools, and things like that, based on open source technologies. And one of those open source technologies, which we are also very actively developing, is Eclipse GLSP, which is a framework that allows you to build modern diagram editors. And I'm looking forward to giving you an overview about that today. As already mentioned, I think Nuno mentioned it before, so please feel free to always just ask questions in the chat. I will try to keep an eye on it, and let's hope to make this an interactive session. All right, then let's dive in. So Eclipse GLSP is short for Graphical Language Server Platform. And basically, it's an open source client server framework that allows you to build modern diagram editors like the ones that you see on this slide here, um, uh, based on web technologies in a way that you can then integrate them either in plain web applications, but also in tool platforms such as VS Code or Eclipse Thea, and even in traditional rich client application platforms like Eclipse RCP or Eclipse IDEs and so on. The general idea that GLSP adopts is coming from the language server protocol, LSP, which you may be familiar with. LSP is extremely popular and kind of evolved to be the de facto standard for developing language support, language editing support in modern IDEs, very popular these days, VS Code, for instance. But of course, so GLSP reuses the same architectural pattern, but adopts it to graphical modeling. And with that, unlocks the same benefits that LSP brought to the programming tool domain, which is GLSP allows to or enables the development of browser-based diagram clients, whereas the front end is really focused on rendering and user interaction. And all the language smarts, the language implementation, model management, model validation, manipulation, and stuff like that is encapsulated in a diagram server. As I mentioned, GLSP is open source. It's hosted at the Eclipse Foundation on GitHub, so you can find it in this URL. And basically what it provides to you is four types of components. First of all, it provides server frameworks. Basically, those are frameworks that you can use to build your particular diagram server on top of it. So your specific server, I don't know, for UML, BPMN, or your domain-specific graphical modeling language can then be built on top of these server frameworks. Then it defines a protocol that sort of describes the messages that can be exchanged between client and servers. And it's very important to point out that this is not like a fixed protocol, but it's an extensible protocol that you can add custom messages to it. And we will get to that more later on. Alongside that, GLSP also provides a client framework. So that, again, is a framework that you can use to build on top of it your particular diagram client for your particular domain-specific language or for your particular diagram language, and define things like user interactions and renderings that is specific to your particular use case. And last but certainly not least, GLSP provides platform integrations. So those are kind of reusable components that you can use to then take a diagram client that you've implemented based on GLSP and integrate it seamlessly in one of the tool platforms that I've mentioned before, such as Eclipse RCP, Thea, or VS Code. So basically, these components then contain the glue code that register an editor, link it to a certain file type, or some other commands and so on. So we will get into more details about that later on, definitely. Right, so how does the communication between the client and the server roughly look like? So essentially, whenever you, for instance, double-click in the File Explorer onto a link for which a diagram editor is registered in the platform, then the first thing that gets active, of course, is the platform integration that triggers basically the opening of your diagram client. And with that, then the diagram client will send an initialization message from the client to the server, which contains arbitrary information that the server may require to identify the diagram you request. Very typically, it's a URI, a diagram type, and stuff like that, but it can be extended to the respective needs of your particular diagram server. The responsibility then of the server is to take this information and load a source model. And the source model is really the data source that you need in order to be able to create a diagram. The source model can essentially be anything. It can be a plain text file. It can be an EMF, Eclipse Modeling Framework model. It can be JSON file. It can be xtext, or it can even be external components that manage a model, like the emf.cloud model server, databases, or even REST services. It doesn't matter as long as you can then, in the next step, in the server, generate a so-called graph model out of that data source. And this graph model then sort of describes structurally how the diagram should look like on the client. So it basically consists of a typed graph model with nodes and attributes and edges, and can be hierarchical in the sense that it can also have one node contains other nodes and so on. And each of those elements inside of this graph model have a type, and they have maybe additional layout properties and so on, in order to give the information that is required on the client, so that the client later then can process this and essentially in the next step then translate that into a picture. For translating that on the client, then this graph model into a picture, we use SVG as a target, and we use the framework called Eclipse Sprody. It's also an open source framework hosted at the Eclipse Foundation. It's a really cool framework that basically allows you to have some sort of model. They call it S model, Sprody model, and transform this into SVG, and then have dynamic functionality on top of that. And that's what we are using in GLSP on the GLSP client in order to translate the graph model into Eclipse, into an SVG. On top of that SVG, then of course there are a couple of editing tools on the client. Basically, that's mouse and keyboard listeners that can react to certain user interaction events and then communicate with the server via a set of actions defined in the protocol to exchange basically whatever needs to be done based on this interaction with the diagram. So for instance, if you create a new node, then you have an editing tool to create new nodes, and basically that's a mouse listener that checks where you are, and then when you click, it will send a request from the client to the server that requests creating this node. The node then, the server then will apply this operation really to the original source model. So that's exactly the source model that it originally loaded, the EMF model, JSON model, or whatever. So it will directly modify that, and then we'll use the same function to translate this updated model again into a new graph model version, and we'll then send this new graph model back to the client, which then updates its view of the diagram. And that's sort of the workflow, or the flow of information that is then typically happening when you interact and change the diagram. Of course, there are a set of default editing tools available in GLSP for creating nodes, creating edges, deleting nodes, and stuff like that. But this is very important. I will talk more about that later. This set of default tools is extensible with custom tools and actions, so that you can add also a domain-specific functionality on top of it that is not just how the diagram may look like, but also how it looks and feels, how the editing tools are set up and so on. Because our experience is that this really is something that you want to have full control over for particular languages. Basically, how this whole interaction and the whole life cycle works on the client and the server is that you have on both the client and the server, you have two independent event cycles. And those two event cycles are connected via action dispatchers that can then send actions not only within one circle, but also over the wire to the server, and then they are processed in this other circle. So the idea is basically, maybe starting from the server here. Let's say we have an initialization message here in the beginning, then some handler will process this message. We have specific action handler for that, that will then ask your implementation to load the source model and transform it into a graphical model. Then we obtain a version of the graphical model. We have a model submission action that is being sent. And for this model submission action, which is called update model action, there is a handler registered on the client. So basically the action dispatcher on the server knows that there is a handler on the client. So it will send this action over the wire to the client, which then has here again an action handler registered for this action to translate this graphical model into the views based on Sprody. And then, of course, the view is updated in the actual browser rendering. And then on top of that, you have event listeners like key or mouse listeners that can then trigger sending more actions. And then depending on your configuration on the very most generic level, depending on your configuration, these actions can either be handled locally on the client only. So basically, that's very useful for things like visual feedback and so on, where there is no server, maybe no server involved. Or they can be sent to the server. For instance, if you request model operations to be applied to the model, then they will be sent to the server. The server again has then particular action handlers registered that can then again update the source model, generate a new graph model version, and do the whole round trip again. So these are the two circles that are kind of communicating with each other. So on the bare, most generic level, and that's basically also open for customization, obviously, on the bare generic level, the whole communication is basically these two event cycles where you have actions and you can register action handlers on either side. And basically that's the most generic layer. On top of this generic layer, you then, the framework already provides certain default implementations of action handlers that you can then just use. And then that you can then basically add, for instance, some data providers that those default action handlers will read. But that's really the most generic layer where the framework builds on top. But you as a diagram editor developer, you can basically decide yourself on which level you want to customize, because both of these client and server configurations are based on dependency injection. That means they are really open to being customized on all levels. And that's really gives you full control in that sense. All right, so that's the very, very generic and theoretic introduction, maybe a little bit too theoretic. So let's have a look at some code. I will show you two examples now. Basically the most simple example to start with, where I just explain the structure, how the projects look like, and how this whole process that I just described looks like in code. And then we will move on to another example where we use much more features than the basic example provides. Both of these examples are open source, so they are available on the GitHub repositories. Basically, the first simple example is one of the project templates that GLSP provides. So it's really a super simple example that should basically just allow you to get started. And then the second one is basically the kind of the workflow example, as we call it. So it's also a very simple diagram editor, but it kind of uses all the different features that GLSP provides. And this is what we use for development and testing new features and stuff like that. All right, let's start with the super simple project example, project template example. I will just pull over one of the many VS Codes that I have open here into this screen. So the super simple example, maybe I should first show you how the how it looks at runtime. So basically, it's here an example that is using Eclipse Thea as a platform. So it's the diagram editor is integrated in an Eclipse Thea application, and it registers a diagram editor for the extension for the file extension task list. Task list itself is just a plain JSON file. I can also show it to you then in a second how this looks like. And whenever you click on it, you get a diagram editor like this one, and it basically just supports one thing, and that's task nodes, these ugly yellowish little rectangles here. And basically, that's all it can do. Of course, you can then already create new tasks by using the palette. You can then also rename things like this. You see also that it currently, when there is no manually set size, it will always choose the smallest size. but it also allows you to resize here elements and stuff like that, and you can do deletion. That's basically the minimal feature set that comes from the generic GLSP framework, and the minimal set to get you started. In this particular project template example, we are using Thea, as I already mentioned, and we are using the Node.js server framework. I will talk about that more later, but GLSP provides two frameworks for creating servers, one for Java and one for Node.js. Both have their particular pros and cons. But in this particular case, I chose to use the Node.js example because this allows me to implement everything very conveniently in VS Code with the same language, and this might be then easier to follow. All right, so let's have a look at the source code. As I mentioned before, basically the client and the server are essentially both two dependency injection modules. So that means in both of these modules, your task is basically to say, to contribute your domain-specific or diagram-specific implementations for certain interfaces or roles in this whole thing, and to pull in the default functionality that you'd like to have. So let's start with the server. So this is basically the dependency injection module for the server. It extends the default diagram module, which is basically just a generic underpinning of it. And what you need to specify is, first of all, the diagram type. So that's just a string ID. And then you need to specify a diagram configuration. The diagram configuration essentially is nothing more than it provides three things in a way. It first of all specifies a type mapping. So that's typically it can stay default, but this is nothing more than basically saying which node and edge types are you going to use in your graphical model. Will it be nodes and edges, or will it be custom nodes and custom edges, and how you want to map those to interfaces so that it's then later on more convenient to work with those graph models, essentially. Here in this example, we just use the default mapping. So if we navigate in here, basically this just says, okay, we have the default graph. So that's just a string graph, which is the type of a node. Here again, a type of a node, here a type of an edge, and we map that onto interfaces, which is then basically just a TypeScript interface to which we map that. So that's nothing special at all, just to provide you sort of like a type level. So that's the first thing, which very often can just stay the default. Then you specify shape hints, and shape hints basically then provide more information for each of those types that we use in the graph model. So in this particular example, we only had one node type. You remember these ugly task nodes. And we specify now how they should behave. So we say, okay, they should be deletable. They should not be reparentable. So that means you can't move them from one container to another because there are no containers essentially. But they should be repositionable. So that's basically that you can move them. Is it this one? Yeah. So that you can move them like that, right? And they are resizable. And that means basically that we can here resize them. So let's try out what happens if I just go back and say now we want this to be false. So we specify here that this node should not be resizable. Then I just need, I think, to restart the server here, go back here and refresh. And now if the configuration, basically the configuration is something that is sent as an initialization from the server to the client. And now you see there is no resize handles anymore. And basically that's what this shape hints do. And the last thing that you can specify along some other details in the diagram configuration is edge hints. So basically it's the same idea as the shape hints, but now for edges. We don't have edges in this example, but essentially you can then specify that this type of edge can be connected to this type of source nodes and this type of target nodes, so that the client already gives you visual feedback when you try to connect those two elements with each other or not, whether it's allowed or not. But please note that these are just hints, so that's why they are also called type and edge hints, node and edge hints, because this is information that the client sends, the server sends to the client, and the client interprets it to be as much as possible out of the box to close to your what you want to have. But the server still always has the last word on what's going to happen. So for instance, if you specify here they are not resizable, the client may for some reason still decide to send a request for resizing an element. So that means then that the server would just have to reject this request and don't do anything. So that means the server is always has the last word on any action that you apply. Aside from that, there is a few details that you can additionally specify, whether you want to have animated updates, or whether we need client layouting. I can talk little bit more detail about that later, but it's essentially whether the server controls all positions of elements, or only or whether the client has certain layouts to dynamically adjust positions. One example is, for instance, here. Now I have set resize to false. Let's just re-enable this again. One example is, for instance, now in this JSON file, we only specify the positions of the nodes, but the server does not specify the position of the label. That's something the client computes based on the layouter. So that's something then where we need client layouting. So that's what's meant by that. And last but not least, there's also this layout kind, which goes in a similar direction. Right, so that's the diagram configuration. With that, the client now knows how the diagram should roughly behave for the default editing tools. The next thing that a server needs to specify is the so-called source model storage. The source model storage is essentially specifying where to load the source model from, and how to load it, and how to save it back. So if you remember this particular, go back to the slides. If you remember that, originally the server needs to load the source model here, and then translates it into a graph model. The source model storage is essentially this communication here, how to load and store back this source model. And the typical way how this is done, let's have a look at this implementation of the task list storage. In this case, it's super simple because we're just loading a JSON model. There is also an abstract class for that provides you functionalities like load from files and so on. But the typical implementation of a source model storage is that we get the request model action. That's the initial action that the client sends that contains the URI and stuff like that. And then we load it from some arbitrary file. And then we put it essentially in a object that is called model state. And this model state is sort of like the only stateful object in a client session. Typically, it's still, of course, located on the server, but it represents a client session where you can put things that you want to store. And obviously, one thing that you want to store in memory is the original source model. So very typically, the pattern is that you specify a custom model state class where you basically extend the default model state. So to specify that I want to store a list of tasks in this case, as this is the example. And then in this load source model method, you basically load it and then put it into the model state. And with that, every other handler, every other component that you may write on the server has access to it, because everyone can get this model state later on injected into their implementation. Right, and the second thing that this source model storage needs to provide is what should happen on save. And in this case, again, it's super simple. Assuming that all changes are going into this task list property of the model state, we basically nothing have more to do than just take this task list and store it back into a file. That's basically it. And last but not least, you can also specify how to create a new empty file. That's in this case just a thing with empty tasks. That's the responsibility of the source model storage. And then finally, of course, yeah, here the model state, so that just specifies which type you want to use as your model state. Basically, it's just extending the default model state and adds properties for storing the tasks. But that's what I wanted to say. Last but not least, what we really need at a bare minimum is the so-called Gmodel factory, which is Gmodel is short for graph model, which is then basically the implementation of transforming your source model into the graph model. So if you want to again take a look at this picture here, so it's essentially how this then should be transferred into a graph model that is then sent to the client for rendering. Very typically, this basically is then very much dependent on the source model format, obviously. So you need to somehow iterate through your source model. In this case, we get the model state, get the task lists, and then we map those to create for each task that we find in this task list. We create a task node, add this task node into the root graph element, and then in the end we call model state update root, and with that basically we send back a new version of the graph model into the to the client, which then renders it. The graph model is built using typically, basically you can build it like you want. There is a number of classes that you can already use from the framework, but there is basically this builder pattern that we typically use, where you say, okay, each task that I find in my source model, I want to create a new builder, assign it a new ID, add some CSS classes. Now I want to add a child element, which is a label. Then I want to specify some sort of layouting algorithm on the client. There is HBox for horizontal box, virtual box, and then you can add layout options like paddings and stuff like that. And then I want to assign a position, that's the XY position on the canvas. And that's basically it. And with that being specified, we can already load file of this format, and we can already show this rendering, because that's all you basically need. So let's have a look at the client, and then I will get back to the questions, I think. So basically what this eventually produces is the graph model, and this will then be sent to the client. So let's switch over from the server to the client. So here again, we have a diagram module. And the diagram module, basically here in the minimum case, doesn't need to specify anything if you just stick to the default graph model elements. So basically it works out of the box because all default graph model elements are already configured correctly. However, what you can do here in this diagram module is to specify additional model element mappings. And in each of these model element mappings, you essentially say, if I encounter a graph model element of type label, then I want to load it as, this is just a DTO, the data transfer object, essentially into an slabel class, and I want to render it with a particular view implementation. And the view implementation is nothing more, here we just reuse a default view implementation, is nothing more than a render method, essentially specifying whenever I find some model element like this, I will produce this SVG from it. Obviously, this can be dynamic and can read the attributes of this element and then produce an arbitrary SVG. And this will then essentially be generated and transferred into the full SVG picture that is being created by traversing through the graph model from the framework, translating each element into SVG and putting it accordingly. Right, and here, of course, you can write arbitrary SVGs, and we will look at that in more detail later. In addition, you can also enable or disable certain features. So as I mentioned before, on top of that, there are certain editing tools, and you can then specify, for instance, okay, that this model element has the edit label feature enabled. By default, maybe it's disabled, but I want to override it and enable it. This is just here as an example, so that certain functionalities can be activated or deactivated for certain elements. In this particular case, this enables us that we double click on an element and then starts editing something. That's it. Right, so that's the minimum that you need to specify. Obviously, and I will show that later, there is much more you can do on the client, there is much more that you can do on the server, but that's sort of the bare minimum. So the only thing that we haven't talked about yet for the functionality that we can do here is creating tasks, moving tasks, and deleting tasks. So what is happening when the client does that, right? So that's we haven't specified that yet. Obviously, that's a server responsibility because the server is in full control. And that's basically what the other things here are doing. Um, Mostly here in the operation handlers. So there you can register action handlers and operation handlers. Um, Basically, both react to certain actions, but we distinguish between an action and an operation in a way that an action is any event that the client may send to the server or that the server internally triggers. And operation is an event that will change the model, the underlying source model. And the reason why we make this distinction is because then we can have special handling for operations so that you don't need to take care of updating the model after you've modified, updating the diagram after you've modified the model. That's basically why there is this distinction. So in the operation handlers, let's just have a look at how something like that is implemented. Let's maybe take the change bounds handler. So that's the one which is responsible when I move stuff or when I resize it. What does it do? They all have to basically implement an operation handler interface. They need to declare for which type of operation they are going to be responsible, in this case for the change bounds operation. Then they can get the model state injected, as I mentioned before. So that's just holding the current state that the model has. And then they need to implement the execute method. And here in this case, we basically iterate through all the new element bounds that the client sent. It can be multiple ones because I can, of course, select multiple and then do something. And for each of them, we basically then change the source model. And that's super important. That's something that people intuitively maybe not think of first. But every change that you do is not happening to the graph model. It can, but it should actually happen to the source model, and then you regenerate the graph model from it to update the diagram. So basically, we get the model state. We find for a particular task ID, we find the respective object, and then we just assign a new position and a new size to it. That's basically the implementation we have here. The reason why it's super important, in my opinion, architecturally to do it this way is that we basically then end up with a unidirectional event flow. Basically, there is no synchronization to be done between the graph model and the original source model because you always run through this process again. Unidirectional transformations, as I'm sure you all know, are much easier to implement and test than bidirectional ones. Sure, you can do bidirectional ones, but they will for sure have more complexity. And that's why in like most of the cases, I would recommend to stick with that route. Of course, the GLSP framework doesn't prevent you from implementing it differently. You can also change the graph model if you prefer and keep them in sync in some way, but that's basically up to your architectural decision. Right. And now I think it's a good time to have a look at the questions that came in so far, since we've covered the most simple example. So Stefan asked, does this have to return the complete graph model, or is there an incremental update? Great question. So the question is, I think, maybe let's go to this, yeah, to this slide. The question is about when there is any change to the source model, we generate a new graph model, and then we send this graph model back to the client. And the question is this always a full snapshot that we send, or is this some sort of incremental model update? By default, it's a full snapshot that we send from the server to the client. Of course, that there is a performance consideration, whether this is a good idea or not. To be honest, in my experience from implementing several diagram editors in the last couple of years, this was never really the bottleneck. So I think also the large diagrams had maybe graph models that were, I don't know, 2 kilobytes of JSON, maybe 5 kilobytes of JSON. And in the world of in the world of modern diagram editors running in the browser, that's not a problem to send these 5 kilobytes on every change. Sure, it can be at some point a consideration, and in this case, I would recommend to look into JSON patch and stuff like that, so that you only send updates to the clients. Would be for sure quite easy to extend GLSP to support that, but there is no default implementation right now. Talking about performance, what we had performance issues obviously with large diagrams, and we've analyzed them. The performance issues, however, were always located on two sides, not on the communication side, but they were located mostly on the rendering side. So rendering the diagram is pretty expensive if it's large, but there are quite easy optimizations that can be done there. Basically, two optimizations that are also supported by default by the framework, that you only re-render what's changed, obviously, and that you only render what's visible. And basically with that, you can limit the number of diagrams already quite a lot. So even if you have a very large complex diagram, so you can basically, when you say, okay, let's say there are millions of these elements here, if I only look at that, I only need to render that. Obviously, there is no reason to render everything else. So that speeds up already significantly. Of course, when you zoom out, when it's a super large diagram and I zoom out, at this point, every element will be visible. But then the other trick is that you query the zoom level, and I will show that later on, and you reduce the detail that you render because it's not visible anyway, right? Maybe for you even less than for me, but I can't read this label. I guess you can't either. So there is no reason to actually render more than just a line, right? So, and that's true for icons, for more complex graphics. So you can reduce the number of model elements also based on the zoom level, and with that also be quite responsive for large diagrams when you have zoomed out. So that's the main bottleneck that I have identified. And the second bottleneck is actually the model operations here and the backend, and that's something that is very much depending on the modeling technology that you're using.
If I can just jump in, I was
Sure.
somewhat less worried about performance. I was trying to work out how you sort of localize change, etc. Right? So if you say you create a new node or things like that, then you want that node to be selected and so on and so forth. So where's that information kept? Is that kept in the graph model that you generate, and so you're then responsible for generating all of that behavior on the server side and generating those updates, or how do I have to think about that?
I see. Okay. So when you create a new node like that, it's actually not selected by default. If you would want to do that, then the server could, after the model update, send a select action, for instance, from the server to the client, so that the client would then select that. So that's one option if you want to keep the logic on the server. But of course, you can also implement it in a way that this logic is kept on the client. And this is maybe also a discussion that we can lead later on, when it's better to do it this way or the other way. You can also basically override the handler for any action that you receive on the client and specify a certain behavior on top. So the typical use case is that you customize the editing tools, and I have an example later on that I will show. That's a very, very common use case, to customize the edit tools so that they do something in addition. So basically, when you click here and then drop, you send the operation. This edit tool is still active at this point. It can wait for the model update to arrive and then do something in addition. So that's something that you can then do on top. But it's a very interesting discussion with, obviously, like all interesting discussions, with no clear answer, whether it's better to implement it as a server behavior or as a client behavior. You can do both. There is overlaps in what you can do, but it's an architectural decision in the end where you want to keep the logic. Very good question.
Thanks.
Sure. So that was the first question. Let's have a look at the second. The second question is, it would be nice to include some of the very useful information in the form of comments with the example code. Yeah, sure. Dimitri, you are of course right. There is a lack of comments in the project templates. With lack of comments, I mean there is not at all comments as far as I know. However, so I completely agree that can be improved. However, maybe I use this to just point you to the GLSP. However, we did our best and spent quite a lot of effort on improving the documentation in general. So there is now this page at eclipse.org GLSP, where there is this getting started page, which essentially points you to the project templates and then basically walk you through what you can do from there. So basically customize the source model, how you can change the graph model generation, how you can then define the rendering with lots of code examples and examples like that. So we've spent a lot of time in improving that, but of course, you're right. More is always better, and especially in the project templates, which should give you a starting point. It would be good to have even more documentation. Good, then there is another comment by Steffen. Don't you need to differentiate changes to the actual model information and abstract syntax? Yeah, visual layout information. With that, you're showing here. Yeah, so the question I think is, please correct me if that's wrong. So basically, whether we are distinguishing when implementing an operation, we should distinguish between the semantic information, like the actual information that is relevant to the model. Maybe if you have a model generator or an interpreter or something like that processing the model, and the layout information, like whether it's located here or here doesn't make any change maybe in the model. Yeah, that's a very good question. And of course, for many, or the vast majority of use cases, I would highly recommend to do it, to separate it, but GLSP doesn't dictate that. So in this super simple example, you have one JSON file, and now maybe it's a good time to show it so that you just have an idea. I think it's here, example list, yeah. So it's basically here, plain text. Yeah, basically a list of task objects. Each one has an ID, a name, a position, and a size. So, and oops, basically you're asking, this should actually not be here, right? And I agree. In many cases, it doesn't make sense to have it here because it doesn't interest most of the processors of this model later on. In this case, for simplicity, we just put it here. It depends a little bit on the use case, but GLSP doesn't care. Basically, you can load whatever resources you like, and in the end, you need to produce a graph model. It's your implementation that you need to provide anyway. However, for the EMF case, so there is, we'll talk about that more later on as well, but for the EMF case, there is also, we provide a notation model base that you can use to store these things, because for the EMF case, it's even more common that you have like already a meta model somewhere, right? And then you just want to visualize it, and then you don't want to come up with a new, yet another notation model. So there is a reusable one that you can use there. Yeah. And Thea, another question by Dimitri. Thea versus VS Code, is it worth investing in Thea given that even Gitpod dropped support for it? Feel free to ignore this, covered later. No, I won't ignore this question because it's super important. I like to talk about this topic. It's not strictly related to GLSP, but maybe we can spend 1 minute on it, even though. So yes, the answer is definitely yes. It's very, very worth spending in effort into integrating with Eclipse Thea. So the question VS Code or Eclipse Thea is really a very a use case oriented one and not a very technical one. The use case when you want to integrate with VS Code is basically you want to be consumable by as many developers as possible who just want to use your diagram editor in their tool. So they want to extend their existing tool with your diagram editor. Then go for VS Code. That's a much bigger user base, right? And there is no need to look at Thea. However, when you think about domain-specific tools and modeling tools in particular, then VS Code is not a good choice at all, because VS Code has a very, very limited way of how you can customize it, especially when it comes to workflows. So it has a very strict API. You can't create a product out of it and then ship this product as a modeling suite or modeling environment. And that's where Thea really shines. And that's where also Thea is used. So these are the very two different use cases. Are you an extension of an IDE or a code editor? Or are you a modeling domain-specific tool, a white label product that you want to sell, I don't know, for embedded and so on? Then go for Thea. So that's the two use cases. And basically that's it. And for GLSP, basically it supports both. Thea also supports VS Code extensions. So basically you could go with VS Code extensions and cover both of these use cases in the end. However, of course, as I mentioned before, VS Code has a very limited API of what you can do. And I'm not saying that to criticize VS Code, it's better to do it this way because this keeps their tool better. But of course, maybe you don't want to limit yourself as a diagram provider to this API. Then you can go to Thea because it is much more customizable and you can design the entire user flow. I hope this answers it a little bit. Okay, so that's about the initial example that we've discussed. So let's have a look at a little bit more interesting examples. Let me just try to find the right editor now. Okay, okay, so we've just seen the most simple example that you can ever imagine, of course. Now let's have a look at other features that VS Code provides. So what I'm showing here is basically, again Eclipse Thea with another GLSP editor hooked up to WF files, these ones. And this is our workflow example that we use. And this basically doesn't make any sense in terms of semantics or whatever, but it shows all the features that you can basically implement with the default implementations of Thea. So you see there is already much more types of nodes. There is these decision nodes and so on. Here you can also create edges, right? You can see also here that we can modify paths of edges. You see here that there is obviously there is on the redo support, even nicer when you move something because then it's animated, right? And there is also containers that you can do. So when you create here a category, you can create an automated task inside of this category, and then it's moved alongside it, obviously, and it's deleted alongside it, stuff like that. So these are all the things that you basically then can do in terms of the node and editing thing. Then there is also edit validation. So the server can add additional validators to give feedback on direct editing. Here also there is a nicer formatting that already uses the same font size and same font size as the original label and stuff like that. Then there is validation integrated, so you can register a model validator. Basically, when you then trigger it, let's try if we can create an error. Yeah. Basically, the server will then send a bunch of issue markers down to the client, and the client will then attach it to the respective model elements. So that's nice. You can then also have hover error messages. You see here these nice projections. So they show basically where errors are and show which excerpt of the viewport you're currently viewing. So you see here, to the right of my current viewport, there's an error, and then you can obviously also click on it and navigate to it. Speaking of navigation, there is navigation support. So you can, let me just double check what the shortcut is, F8. You can implement arbitrary navigation commands. And with that, I'm hitting now F8 all the time. We navigate through all the elements. Maybe you don't see it very well, but it's essentially then also selected. And you can register on the server so-called navigation providers, navigation target providers, that link an arbitrary request, like go to definition, go to implementation, go to documentation, and link a specific resolver to that navigation. And with that, you can then resolve an element based on that and return it. With that, for instance, go to next node, then we jump to this one, right? And you can also jump outside of the diagram, go to documentation. Here, the server then provides a URI that is not the diagram. And basically what then GLSP client will do, it delegates it to the platform it is integrated with and say, can you process that please? Because I don't know more than my diagram, right? So you will navigate to that file here, and it even highlights already. I can basically also specify what to highlight and so on. Right, then you have things like, marquee tools, stuff like that. You have auto formatting, auto layouting. Let's maybe just do that. So it's integrated with Eclipse layout kernel and stuff like that. Then you have all these things like align, center, resize, and so on and so forth. So there's lots of things that you can actually do. And to also mention a little bit platform integration. So in the Thea case, all markers that are received by the diagram will also be delegated to the platform itself, so that the platform can also show it to the problems. And then when you click on it here, it will also select that. Good. So that's a couple of more features that you can do. Obviously, also you can also then from the platform navigate to a specific diagram element. So I think there is some example that we have here, a command that we register here, open example one as the task push. So as you see here, we directly jump now to this push element. That's, by the way, something that you can't do in VS Code, because in VS Code you are limited to the URI. You can't extend it. So that means you can't add additional information. So that's one of the limitations that is currently there in VS Code. Right, so how is all this implemented? Essentially, like all of what I showed is basically server-side implemented. Now switching to the IDE where this workflow diagram server is implemented. So as you see here, maybe also one tick larger. This is now in Java. You see the structure is super simple. We again define a workflow diagram module which extends some base. It has a diagram configuration, defines a model storage, defines a factory. And now it starts where it gets interesting. So there's much more operation handlers. Basically, these are all defining what actions you can apply or what operations you can apply. Here we use the default palette implementation, which basically reads through all registered actions. And if there are extensions of the create node actions, then they would put it automatically in this node section here, and the same for edges. But of course, you can override it. And to be honest, most of the people override it because they want to have full control, irrespectively of the handlers that they register how the palette looks like. Then there is things like pop-up factory. So that's defining what should show up when you hover over something. Model validation, basically, as you can imagine, it's all an interface that you need to implement. There is also then hopefully some documentation, what you need to do. And essentially here you get a number of elements, and you need to provide a list of markers. And those markers are linked to an element and so on. And so on and so forth. So that's basically all the different implementations that extend and implement this particular behavior. The idea here really is you extend a default generic base module here, then you need to provide this bare minimum stuff. Then you have operation handlers that you can add, action handlers that you can add, and then the idea is that you go here and hit control space, and then you see what else can you actually do in this case. I want to now I don't know, add a label edit validator. So you override this bind label edit validator, and then you immediately get an implementation like that and see, okay, I need to provide a class of this interface, and then you create this class of this interface, and then the interface should tell you what you should do. That's the basic idea, how this is designed to work. Right. I think with that, I hopefully gave a little bit of an overview of how this looks like. Let's go into some more topics that I wanted to highlight. Just double check the time real quick, because I didn't look at my clock before. I don't want to over exhaust your time. Okay, we have still half an hour left. That's great. So one thing that I wanted to cover a little bit is the question of how GLSP relates to LSP and what is very specific to diagrams, and why can't we just take LSP and are good, right? And still apply to diagrams. And I think that's quite an interesting discussion, and that also is kind of the justification or the reasoning why the architecture is here and there a little bit different. And that's what I wanted to discuss a little bit about. So essentially, when you think about the architecture of LSP for textual languages and GLSP for graphical languages, the main architecture is kind of the same, right? So you have a client and you have a server, obviously. However, there is a lot of big differences. So for instance, the client is super generic in the LSP case, and it is not really 100% generic in the GLSP case. And this is because in the diagram world, we kind of need this rendering flexibility. While text is always just text, whether you're writing Java or Python code, basically it will always look the same. And that's not true for diagrams, obviously. So here you need full flexibility and power to actually render diagrams in different ways. This is why the client is not 100% generic. Of course, you could put that information or this logic also architecturally, theoretically on the client and have it transferred to the, on the server and have it transferred to the client. But that would add a lot of overhead and complexity, given you're running in a browser anyway, and you can reuse the same framework in the browser in many, many use cases. So it doesn't feel worth this abstraction layer that you would have to introduce in this case. So that's the reason for the non-generic client. The second thing is editing works very differently in diagram editors from language to language. So for instance, there is languages where you can move elements freely, essentially, but then there is also languages where you have very constrained editing scenarios. So one example here is this ladder diagram example, where you can't just move this around, but you can only drop it from one rail to another rail and so on. So there's a lot of constraints going on. And that's, of course, very specific to this diagram type. And of course, that's not true for text. You can have always the same text operations. There's always lines, and that's basically, and lines and characters, and that's basically it. And what that means is that you have in GLSP full editing, full control over your editing tools, so they are extensible. The UI is extensible to hook up domain-specific UIs and controls. I will show that as an example of that later as well. And there is this diagram configuration on the server. So that's basically, there is this reasoning. Here again, as I mentioned before, of course, there is a trade-off. How much logic do I want to put into the client, and how much logic do I want to keep on the server? And that's really an architectural decision. So maybe for migration use cases, you try to keep as much as possible on the server because you have it already, for instance, in your Java-based implementation, and you want to keep it there. There you put more responsibility to the server. If you build it from scratch, maybe it's easier and more direct to implement certain things on the client. So it's then the server more becomes like a model management and diagram management server, and not much more about defining exactly the behavior of the client. So it's a little bit of a trade-off. And last but not least, and that's, I think, the reason for this most significant difference architecturally between LSP and GLSP. So in LSP, the only one who can write is the client, actually. So the client reads the file, and when you change it and save it, the client writes it back to the file system. The server is just an observer, so it really just reads the same file system, and it will then basically just react to the changes that the client sends to it that it did before, right? So to keep them in sync. And the reason for that is you typically want to have only one responsibility, or one responsible component, obviously, to read and write, and have basically the controller of this resource. And for LSP, it can be the client. But for GLSP, it's not that simple, right? So in modeling tools and diagram editors, you have a vast difference of formats that you want to read from, like EMF, whether it's JSON, whether it's REST, whether it's model servers like the one from emf.cloud and so on. So there is really basically a lot of formats that you need to support. And there is processing between what you read from disk and what you show on the client. So there is sort of like an impedance mismatch. You need to transform this into a diagram before you can actually show it to the user. And that's not the case for text, right? So the client doesn't need to understand the format or the language in order to show the text. For diagrams, that's different. And that's why we chose to put this again. Of course, you want to have one responsible component, and therefore we chose to put this on the server. So the server is responsible for loading, interpreting, mapping, and manipulating. That basically makes the client very stupid when it comes to the actual model management. Still, of course, you need a common artifact and a common language that the client and the server communicate based on. So what's the thing that both of these know and that they use to communicate, and that's the graph model. So in LSP, that's basically lines and characters, and documents. So the LSP client says to the server, give me the location of the definition of the symbol that I'm currently on, without knowing actually where you are currently in terms of the language, but you know the character and the line and the document. That's basically what the client knows and sends to the server. And the server then knows the abstract syntax tree and stuff like that. And then we'll send, for instance, the definition of the particular symbol, which the server only understands, the definition of the symbol to the client, and the client just stupidly opens another text document location. As the common artifact and level of the communication is the graph model. Sorry, it's the text model. And in GLSP, this is the graph model. So when the client deletes something, it doesn't, of course, know what the original model element this has been generated from, but it knows, for instance, the ID of this graph model element. So it will say, I want to delete that. Whatever you do with this information is up to the server, right? So that's then the design decision that is taken here. Right, and with that, I wanted to go to the last, I think, most important aspect of GLSP, and here I will also give a little bit of more demos and examples, and that's basically why flexibility is key, and why this is a little bit different than it was in the traditional world where we had GMF and all these other technologies in the traditional Eclipse ecosystem, rich client ecosystem. And that's, in my opinion, when I look back over the last couple of years of the projects that we did, that also, of course, significantly impacted the architecture and evolution of GLSP. It's mainly because this whole LSP and GLSP is not just a mean to get onto a web technology stack or to get into a cloud. Of course, this is a very good reason to do it, but it's not the only reason. It's basically also an architectural paradigm shift. So when you think of it, the modern tool technology stack like VS Code, Thea, they are much more fluid and diverse as the Eclipse Rich Client ecosystem. Because with VS Code and with Thea, we are currently dealing with very different scenarios, like you want to run ephemeral workspaces in the cloud, but with the exact same tool, more or less, you want to also interact with want to install it on your local system, interacting with your local file system. Then again, you want to use the same tool to interact with some model server to do some collaborative stuff and so on. And you want to reuse as much of the components as possible in all these very different scenarios. So what's really becoming much more important with these very different ways of deploying the same components is modularity and combinability. And I think that's really key for this new technology stack and new architecture that is being used there. And of course, this is not only true for code editors and IDEs, it's even more true for diagram editors, because diagram editors are very specific by nature, very specific to a diagram language, that because they are typically targeting a specific domain. This domain uses very specific data sources, maybe not only models, but also other tools that they want to integrate. They have very different workflows depending on which domain you ask. Some generate parts of the model initially and then generate something else. Others create them from scratch and have an interpreter in the backend and stuff like that. So it's very, very different. And last but not least, there is this, as I mentioned, integrations with other tool components. So it's a very, very, there is a very high need for having flexibility as much as possible to be able to address all of these different scenarios. And what I did then is basically taking this idea of the flexibility theme and walking through each of those components that we've all now in the meantime know, and give one example of where this flexibility I think is very crucial looking back at the projects that I did. So obviously the first flexibility starting here with the client is the direct access to the base technologies to have full flexibility and control over look and feel. And that's actually something that GLSP in the beginning didn't have that prominently. So there was some sort of abstractions there. But over time it evolved that we actually more and more evolved to giving direct access to the base technologies where flexibility and where control matters. And that's the editing tools, the UI controls that you want to have there, and the SVG generation and CSS. And in the end, it turned out that this is actually much better because I mean these base technologies, they are great, they're excellent. Why hide them in some sort of abstraction? Everyone knows how to write HTML or create SVGs. It's rather simple to do. You benefit from the excellent debugging tools that are already out there. And that's actually one of the reasons why we wanted to move to this technology stack in the first place. So we kind of evolved to not hiding it anymore, but really embracing that you want to interact with those directly. And as an example, where this has been used, let me just find this now here. Yeah, so one thing that you can do it basically is you can fully customize the editing tool. So if you remember, we can create here a manual task, for instance. Why can't we anymore? Maybe I broke something. Let's just reload and hope it works now. Create manual tasks. Maybe I killed the server somewhere. Where is Eclipse? Let's restart the server. Made some changes. Interesting. Always great to do some changes and then have hot reload probably on. Let's see if it works now. And create a manual task. There is a breakpoint. For some reason, I clicked somewhere on the breakpoint. No. Good. So we can create manual tasks and we can create those edges, for instance, from here to here, right? So that's the default tools. But if you want to provide some more flow for the user, maybe the users don't want to click here and then select the source and the target, but they want to directly start from here. And maybe to help the user even more, you want to highlight all the available targets. So you can do that very easily by just adding additional editing tools. So as an example here, when I hit the Alt key, you don't see it right now, but you have to trust me on that. I can select directly from an element and then already jump into this mode where we create an edge, and I can already highlight the targets. Here I use some fancy disco 80s CSS animation just to show you that you can really do quite cool stuff with those base technologies. And then you select the element, and then this is done. Basically, this has been implemented, and I can show you the code, but I think in the interest of time, I won't have too much time to go into detail. But essentially, it's just adding another editing tool. So I encourage you to extend the client to benefit from this functionality that this technology stack provides you. Also, you can have dynamic SVG views. So I already showed you, essentially, views are translating an element from the graph model into SVG, but they can have logic and take a zoom level and stuff like that into account. So you can also, for instance, to specify who is actually responsible for this manual task, the user can then zoom into here and then see an ugly face in this stupid example, and then render it. And when you zoom out again, you just hide it again, right? So that's, I know it's a stupid example, but it just give you an idea that you can make use of that by just making the views a little bit more dynamic. Right. Also, where flexibility, of course, really matters is the platform integration. And that's basically whether you're integrating in Thea or in VS Code. And we covered this topic a little bit. That's why I will keep this one short. Basically, you can, so the idea of these platform integrations is that they only cover what's really platform specific, which is typically editor registration, global menus, and platform styling, but do that using the native API, obviously. So the native Eclipse API, VS Code API, Thea API, so that you are kind of have the full power of these underlying APIs. So everything that is platform specific goes into that, and everything that is not platform specific goes into your diagram client, which is completely independent of the platform. And the idea is that this is then extended by dedicated your integrations. For instance, here your integration into the Thea platform, which of course builds on top of the generic Thea integration, which then of course has the dependency to Thea, and then integrates that by a dependency to your diagram client. That's the idea how this is typically done. That doesn't mean that, for instance, of course, the Thea integration can then send actions in typically, so that works perfectly. And even your diagram client can expect certain functionality from the platform, whatever it is where it is integrated in, by declaring some interfaces that these integrations need to be binding, and that you can basically then replicate for other platforms as well. The important thing here is this platform integration and the flexibility here is just as important as the diagram itself, right? Because a good workflow in a good modeling tool doesn't start and end at the borders of your diagram editor. It starts when the user opens the tool and works through his or her process. So that's why it's super important to have full flexibility here. Right, so now let's go to the server side. Here, the flexibility that I wanted to point out, one flexibility that I wanted to point out is model management. So especially with the 1.0 release, we spent quite some time in making this pulling this model management related stuff completely out of the core, in the sense that you have now full flexibility, and it's basically your choice how you implement your model management, what format you use, what framework you use, whether it's local or remote, whether it's a service that is shared across users or isolated. Basically, that's completely now in your hands, and you are that of course also means that you need to implement it or that you need to bring it to the table. That being said, GLSP now pulled out all these things that are very common and reusable, like the ones for the integration for EMF, for JSON, and for emf.cloud, into reusable base modules. So basically, this can be pulled in like this for now. And of course, that's super important because it facilitates migration, for instance, from your current tool to GLSP, but just as important, to not lock you into a certain model management framework. When you decide to go with GLSP, you can still go from EMF to JSON in the future or whatever you like, right? And what's also very interesting, it enables reuse across multiple deployments. As I mentioned in the beginning in this flexibility slide, what I see a lot is that the same diagram client and the same diagram server is actually used in different contexts. One as a local tool interacting with the local file system, but then also integrated in a web application where you have maybe a shared model management or a shared model server where people then can at least read for documentation purposes models and so on. So it's a different model management in this case because you read it maybe from a REST service, but you can still reuse a lot of these parts, even though the model management is now completely different. Right, so here I just wanted to mention one thing that is quite typical, especially for the modeling guys, is to use EMF. And then, of course, there is one component that I just wanted to mention because I mentioned it here and there. That's the emf.cloud model server. I won't go into any detail, but basically the idea is that you typically have multiple widgets in your tool interacting with the same underlying model. And emf.cloud model server essentially provides a component that loads and manages these runtime states of the model so that they can be then interacted with from different widgets with different services, like a GLSP editor, a JSON Forms editor, and an LSP editor. So they all essentially manipulate overlapping parts of the model. Of course, they don't want to share state with each other directly, and that's why this model server is a good idea in certain use cases to encapsulate this model state. So essentially, if you know EMF, it's essentially a replacement of the editing domain in this distributed architecture. But I'll jump over that for now. Right. Last but not least, I think we have a couple of minutes left, and I also want to answer the two new questions. Last but not least, the GLSP server framework. So I've already mentioned there is now Java and a TypeScript framework. The TypeScript framework is rather new. Um, and obviously, it's up to everyone to use whatever they like. You can even write one from scratch as long as there is some protocol message support and I/O. That is fine. You can even use Rust if you like. But of course, it's much more efficient to start from a framework. And now with TypeScript based framework, it has a very big advantage for use cases where you are targeting VS Code, for instance, where you can't expect a JVM to be installed on the user machine, and that opens a lot of or removes a lot of requirements. And it opens the doors to new deployment options, and that's the last thing that I wanted to highlight, because now you have a lot of different deployment options. That's just the ones that I'm aware of right now. So which tool, which server is being used, and which model management framework. That's just I wanted to mention. But of course, also you can decide where you put the respective behavior now in terms of does it run in an own process, is it in a separate process, is it in a separate container, and stuff like that. So obviously in Eclipse it makes sense to have everything running in one process if your server is Java based, whereas in VS Code is typically a separate process running in Node. In Thea, for instance, you can then in a cloud deployment have this in a separate Docker container. You can even then go as far as extracting yet again the model management in a Docker container, which then maybe even can be shared across multiple users and stuff like that. So that opportunity also opens up. And last but not least, and that's where I also want to show a demo, a TypeScript-based server also opens up use cases and deployment scenarios where you don't have a backend at all, or where you really want even to where you want the server to be running in the front end. That means in the browser, and there is good use cases for that. So I'm sure you can think of documentation use cases where you have limited functionalities and so on. And one popular use case is, I'm sure you've seen this before, you can go to any GitHub page now, right? And you can then just click dot, and with that you open a lightweight VS Code, if you want to call it like that. It's GitHub Dev. Essentially, it's a VS Code running only in your browser. And oops, I will just close that. And it's running only in your browser, and there is no backend in the cloud whatsoever for this, right? So the only thing that there exists is a way, an API to interact with the file system that is living in the GitHub repository, essentially. So there is no backend, but still you can build a TypeScript-based GLSP server now in two ways, either node-based or Webpack-based. And with Webpack-based, then you can even deploy them only in the browser, so that you can then even open diagram editors, just the same one that we've seen before, running only in the cloud without any backend whatsoever. So that's pretty cool, I think, and that's showcasing the flexibility. If you show that to non-techies like us, then they say, okay, that's the same thing I saw 5 minutes ago, or what's the deal, right? But if you know what that actually means, it's really cool, right? So there is no backend at all, and you could just run the same thing also just in the browser, and that's cool for certain use cases. Right. That brings me to my last slide, but before I go there, maybe let's just look at the questions to have as much time as possible for them. So Dimitri asked, does GLSP support multiple diagrams per model? Does GLSP support both canonical and non-canonical diagrams? Very nice questions, yeah. In general, the answer to both is yes, but you have to do it on your own. So there is no first-class support for multiple diagrams in one model, so that there is specific thing that you need to implement or so. But since you are responsible of providing your model management implementation yourself anyway, in a sense, so basically you need to decide where to load your model from and how to create your graph model. If you take that into account, sure, it's no problem to implement it. Essentially, the way how this would then need to work is that the different diagram client implementations, they just need to connect to the same GLSP server, and that's very typical, right? So typically you run one GLSP server instance per tool instance, and if you have multiple widgets or editors open, they communicate to the same GLSP server instance, and that's what you then can leverage, because they can of course share state with each other. That is when you are living inside one GLSP server. So that means yes, you can implement that, because what's crucial is of course that you both can edit at the same time, right? So you need a way to serialize those changes so that you don't conflict with each other. Does GLSP support both canonical and non-canonical diagrams? Yes, basically how you transfer the model into a graph model and update the client, and when you do that, that's completely up to you. So you can also basically overwrite or have a very canonical way. So whenever a new model element is created, you automatically create a new diagram element for it and stuff like that. So that's basically then GLSP server behavior that you would need to implement. One thing that I wanted to mention here, yeah, that's the same with whether you're using auto layout or not, and when to change the how to deal with the graphical changes. So that's really up to you. But of course, that always means you need to implement it yourself. Um, 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 um. Yeah, maybe one thing that I can even show that's interesting. Um, so you can very easily add custom controls here as well, right? So here is an example where I just now show an HTML on top of the diagram. And with that diagram, with that HTML, it fires an action that is then sent to the server. And the server will then generate a new diagram, set the diagram state to read only, and update the client with that. And when I do that, for instance, you see basically it jumps between the normal editing mode, and then it jumps to a filtered view, which is not editable, so I can't change anything here, right? So that's basically with there is no custom behavior or something that is needed for that, other than how to create the graph model. And that's what you can leverage also for canonical diagrams in a way, I think. And that mechanism is pretty cool to show some certain views, like show me all incoming references and stuff like that. So the server can at any time send an update model to the client will just render it. Right, then there is a question. Are you aware of any integration between GLSP and Eclipse J? No, but it's also not really needed. So there is no integration or dedicated integration between Eclipse GLSP and J. Because J is really just a workspace management framework or component, where the tool that you deploy is actually kind of independent of J. So you can in J use VS Code, you can in J use Thea, you can in J use even IntelliJ. GLSP has integrations rather with the tool platforms like Thea, VS Code, and so on, not IntelliJ though. But I guess they have a browser widget, so it could be done. So that means that's the level where GLSP integrates with, whether it started with J or whether it started with Gitpod or any other workspace service. That's basically doesn't matter to GLSP in that sense. And the last question, also from Dimitri, in the Java EMF version of the GLSP workflow, of the workflow GLSP server, the workflow model extends classes from GLSP graph eCore. Are you aware of Java EMF examples where the DSL meta model is standalone? Yeah, so there is I think an important distinction. So the question is, there were some dependencies to a particular GLSP specific meta model, this graph eCore, and whether I'm aware of use cases where there is a standalone meta model being used. And yes, definitely I am. There is a very important distinction. This graph meta model, this graph eCore, is just an EMF-based representation of the graph model that is being sent from the server to the client. So it's rather a technical means that GLSP chose to use EMF for representing the internal state of the graph model, but it doesn't have anything to do with your source model. So your source model can be an arbitrary EMF model or whatever other model. standalone meta model, and so on. And you need then to just transform it with the G model factory into this graph model, because that's the language that the client and the server share to structurally describe the diagram. So basically, the graph model is just a mean to define your graph model, your graphical model, and the state of it. You can extend it by extending the meta model, but that's typically not necessary. But it's really just a technical means that GLSP chose to use EMF here, but it doesn't have anything to do with your source model. Right, I think that was the last question. So in that example, extending the meta model is an easy way. Yeah, sure. Definitely, yeah. Good. Then let's come back to the last slide. Oh, sorry. And we are then almost finished with the time. Anyways, about a point scheduled landing. So conclusion. Yeah, so I believe flexibility across all levels is really key in this modern technology stack, and I think we should embrace it and embrace also the base technologies instead of hiding them, and really try to find new creative ideas to support these different multiple deployments, new ways of providing diagram editors and modeling tools in general to the users. There is a great potential here to include even more people in the modeling process, in my opinion, and to make it as easy as possible to contribute to it in one way or another. Whether it's a full-fledged tool for an engineer installed on the local system, and then the same model can also be with rather the same components, but maybe a few of them slightly adapted, also be accessed in a very lightweight way using the browser and stuff like that for documentation purposes and so on. So there's a very great opportunity here. And I would really kindly invite you to get started with GLSP, have a look at it. I think it's now rather easy, especially compared to the past, since there is now some certain API stability and better documentation and project templates. However, of course, getting started with a framework is always a little bit challenging. So please also feel free to get in contact with us. So we provide a couple of ways how you can contact us using the GitHub discussions and stuff like that. And I invite everyone to try it out. Feel free to contribute also and open discussions for future enhancements to cover your use cases there as well. Thank you very much. I was very happy to be here. And if you have even more questions, just let me know. Happy to answer them.